Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 2.4, Complex Numbers. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. The complex numbers represent all numbers that we know of and even some that we don't know of. But before we look at what the complex numbers are, let's start from the bottom and build up the system. The natural numbers are the set of finger counting numbers, or the digits. So when you start counting on your hands, you count on 1, 2, 3, 4, 5, etc. So the natural numbers are those numbers, and here are some examples. 1, 17, and, well, this number. The whole numbers are the natural numbers plus the number 0. So we could write the whole number set as W for whole, including the element 0 plus all of the natural numbers. And the natural number examples, including the number 0, would be some examples. The integers are the set of positive and negative whole numbers. So that would be the positive and negative natural numbers plus the 0 that we found in the whole number set. And some examples are negative 3, negative 2, negative 1, 0, 1, 2, 3. Now I'm going to use I for the integers, but the technical set name is Z, coming from the German word for integer. The rational numbers is a set of fractions or ratios, quotients which are formed from the integers, where the denominator is non-zero. Of course, the denominator must not be 0, because then the fraction would be undefined or indeterminate. And if we look inside the word rational, we see the word ratio. We also see the word ratio inside the word fraction. And so we are clearly talking about a ratio of two numbers. The two numbers whose ratio we are taking are both integers, except the denominator is not 0. An interesting thing happens then to the rational numbers, and that's when we express them as a decimal, the decimal either terminates or repeats. And let's just take a look for a moment at a repeating decimal to see what happens here. Let's express the decimal 2.091, where the 91 is repeating, as a fraction. One strategy to do this is to let x equal 2.091 repeating, and then we recognize that if we multiply by 10, we move the decimal 1 to the right. If we multiply both sides by 100, we move 2 to the right. And if we multiply by 1,000, we move the decimal 3 to the right. Well, let's just multiply by 1,000 so that we would get 2, let me just express this actually as 2.0919191, and I'll put the bar for the repeating over one of these 9 ones. So if we multiply by 1,000, we get 2091.91 repeating. And if we multiply by 100, or rather just 10, we see that we get 20.919191. So if at this stage we were to subtract the top number minus the bottom number on both sides, then we would get on the left-hand side 1000x minus 10x is 990x. And on the right-hand side, the repeating decimal part is the same, so we're left with the integer 2091 minus 20, which is 2071. And from here, we can express the fraction for x, which is the same as the decimal 2.091 repeating, as 2071 divided by 990. Now, except for checking to see if we can reduce, this is our final answer for the decimal 2.091 repeating as 2071 over 990. Let's just go to our graphing calculator program and confirm. So let's enter our fraction 2071 divided by 990. And I'm going to, if I just enter that, I can see it tries to give me the fraction in reduced form. But if I put a decimal place in one of the digits, then the calculator will approximate this. And it'll approximate as a decimal, and I can see 91919191. If I change the number of digits in my expression, then I could see this going on with more 9191s instead of rounding up to 2, because each 9 would round up the previous digit to a 2, and that's why we're getting the 2 here. So I feel fairly confident that we've got the right expression. 2071 over 990 is the repeating decimal 2.091919191, etc. All right, let's go back and take a look at the next number in the number set. After rational numbers, we have irrational numbers. And the IR here, means not. Now, notice that we used the letter Q to represent the rational numbers because Q stands for quotients. Here we're using the symbol Q with a bar over top, where the bar means not. So we are talking about numbers that are not rational. So the not rational numbers, or the irrational numbers, are numbers that never terminate or repeat as a decimal expansion. And it's best to see some examples here. Some common examples are pi, which we often say is 3.14, but that is just a decimal approximation to the irrational and therefore never ending and never repeating decimal of pi. We also know E, an irrational number, that is the natural number, is approximately 2.718, and we will see E showing up in population growth and anything that grows proportional to how much of the quantity there is. This is known as the natural number. And then square root of non-perfect squares, logarithms of non-perfect powers of the base, certain trig functions or inverse trig ratio values, inverse trig function values. So let's move on to the next set of numbers. When we combine all of the rational and irrational numbers, we get the real number system. And when we think about the number line, if I ask what is the next number after 1, a lot of people will say 2. But that's if we're only considering the natural or the whole or even the integer number system. But really the next number after 1 is so close after 1 that between any two numbers that I think I've found, I can always find another one in between. So in fact, there is no next number after 1. There's a next integer, or a next whole number, or a next natural number. But the rational numbers, there is no next rational number, and therefore there is no next real number or irrational number. So these are some different examples of all of the real numbers. Up until now, we've been working primarily in the real number system. And in fact, we've been spending a lot of time graphing in the real plane. We've been putting real numbers along the x-axis and real numbers along the y-axis. But we are now going to look at what happens when we don't have real numbers. Let's just take a brief moment to remember when we talked about defined, undefined, and indeterminate numbers. We had expressions like y equals 0 over 3, which meant that y was defined to be 0. And if y was 3 over 0, then we said that y is undefined. And we've had a little bit more exposure to know that this means y approaches positive infinity or negative infinity, depending on if this were to come from a graph, what the sign chart might be, or what might be the expression that led to the undefined value. We might also get y equals 0 over 0, which led to y being indeterminate. And an indeterminate number means infinitely many values, which led to a whole so that the graph could actually be a function. But we also said, apart from the domain restriction that denominators can't be 0, which would actually go under this category, denominators can't be 0 because we either get undefined or indeterminate. We also said that radicands of even roots must be positive or equal to 0. And in this case, we are starting to take a look at what happens. If we take the square root of negative 1, in the past we've said that there is no number that we can multiply by itself to get a negative, because positive times positive is positive, and negative times negative is positive. So there's no number that multiplies exactly by itself to get negative. But now we're starting to consider what if we wanted to solve something like x squared plus 1 equal to 0? If we did that, x squared would equal -1, and so x would equal plus or minus the square root of -1. Well, what if we wanted that to be something? We could decide to let the square root of -1 equal a quantity called I, such that when you square I, you get -1 back again. And that's exactly what we've decided to do. So radicands of even roots have to be positive or 0 if we are working within the real number system. But as soon as we are looking outside of the real number system, it's possible that we can take the square root or fourth root or sixth root of a negative number. For the purposes of our graphs, we will always be graphing in the real plane. So it is still not possible in the real plane to have a radicand of an even root that is negative. But for the purposes of solving equations more generally than in the real number system, it is possible to have a radicand of an even root that is negative. So let's go back and take a look. The imaginary numbers are based on the set of numbers where I is defined to be the square root of -1. And therefore I squared is equal to -1. So the imaginary numbers is the set of non-real numbers that solve equations of this form. And if we solve equations of this form, we have x squared equal to -r squared, where r is a real number. And if r is a real number, then r squared cannot be negative. So the negative multiplied by r squared guarantees that the right-hand side is a negative number. When we solve for x, we end up getting the usual absolute value and the square root of -r squared. So the absolute value of x equals the square root of -1 times the absolute value of r. And then the absolute value here is going to give us a plus or minus with the r. But then, let me put the r in front. But then the square root of -1 we have decided to define as I. So we get our solutions of x equals plus or minus ri. So the imaginary numbers, we are using the set of r for real with a not, so not real. The numbers that are not real are imaginary. And they are of the form a real constant times the imaginary basic number of I. So examples are 2i, -2i, the square root of 2i, and then the pi I. Do notice here that the I is not under the square root. When we take the set of real numbers and the set of imaginary numbers and join them together in a certain way, we get the complex numbers. The complex numbers, we will use the set C. And C is a combination of numbers that are both real and imaginary, and they are of the form a plus bi, where a and b are the coefficients that are both real numbers, and I is the same square root of -1. So some examples of a complex number is any number you can think of up until the real numbers, and then the imaginary numbers, and combinations of adding real and imaginary numbers together. We often plot complex numbers like 3 plus 4i, not in the real plane, but in the complex plane. And what we do is we talk about the real part. If this is a number, let's call it z, we can talk about the real part of z, which is 3, and the imaginary part of z, which, while we think it might be 4i, it's just the coefficient of the imaginary part, and it's 4. So we plot the real part of z along the horizontal axis, and the imaginary part of z along the vertical axis. And this allows us to take a one-dimensional number, but to plot it into two-dimensional space. So we plot 3 along here and 4 along here, and we get the imaginary or the complex number of 3 plus 4i. We may be interested in doing other things like finding the modulus of that number, and we find that the modulus of the number happens to be the square root of 3 squared plus 4 squared, which is just Pythagorean theorem to give us 5. All right, well, let's take a look at some examples involving the number system. Let's draw a vertical flowchart of the number sets, starting with complex at the top. Our complex number system breaks into the real number system and the non-real number system. So this might be an example of a number 3 plus 4i. Only the 3 belongs to the real numbers, and the 4i belongs to the imaginary numbers. We stop the imaginary numbers here. The real numbers, however, are broken into the rational numbers and the irrational or not rational numbers. The irrational numbers stop here. The rational numbers then flow down into the integers, which is also given by this set name, and the integers flow into the whole numbers, and the whole numbers flow into the natural numbers. So any number you can think of can always be called a complex number, but depending on the path that it follows, it may be called a rational, irrational, real, or non-real. All right, let's solve for x. From this equation, we see we have a quadratic, and of course a quadratic equation, ax squared plus bx plus c equal to 0, always has solutions of the form x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we can refer to this quantity here as the discriminant. The discriminant is called the discriminant because it discriminates between whether we have real or non-real solutions. If the discriminant is positive or 0, then under the radical we have an acceptable quantity for real numbers and we get a real solution. But if the discriminant is negative, the square root of negative will give us an imaginary number. And then combining the imaginary part with the real part would give us a complex solution. So depending on whether the discriminant is positive, negative, or 0, we can discriminate what kinds of roots, and therefore what this means to the graph for the quadratic function. Well, we don't see that this is exactly a function, but if we had imagined this was y, and we had set y equal to 0, what that means is that we are looking for x-intercepts of y equals 2x squared plus 3x plus 4 when x is equal to 0. So we can link the graphical with the algebraic. All right, so let's go ahead and solve for x from this quadratic. Before I try factoring, I want to see what the discriminant is. So the discriminant is b squared minus 4ac, which is going to equal 3 squared minus 4 times 2 times 4. And we get 9 minus, this is going to give me 16 times 2 is minus 32. And this is equal to negative 21, which is less than 0. Because the discriminant is less than 0, the quadratic function, or the equation, has complex roots, or complex solutions. So let's go ahead and use the quadratic formula then, because we won't be able to factor with the negative here. And we can put the negative 21 directly under the square root sign. So we have x equals negative b, so negative 3, plus or minus the square root of negative 21, all over, oh, let me just make sure that I've subtracted carefully. I think this is negative 23. And this should be 23 in here. All over 2 times a. A is 2, so 2 times 2 is 4. And when I get my two solutions here, I get x either equals negative 3 minus, well, the square root of negative 23 is really the square root of negative 1 times the square root of 23. And I'm going to refer to the square root of negative 1 as I. And I'm going to take that I and put it in front of the square root of 23. So negative 3 minus I square root 23 all over 4, or negative 3 plus I square root 23 all over 4. The reason I'm not putting the I at the back is because I don't want to mistakenly put it underneath the radical sign. Let's use our graphing calculator and confirm this solution. On the graphing calculator then, we are going to go to Solve, which is in the catalog menu. And I happen already to be there, but if not, you can scroll down or you can just type any letter here. That will take you to the top of that alphabetic list. Now solve might be closer to T, so you might want to go to T and scroll up. So we find solve. The syntax or the grammar for this function is to write the equation and then comma the variable inside the brackets. So the equation is 2x squared plus 3x plus 4 equal to 0. You can't have an equation without an equal sign. And then comma, the variable of the equation, which is x. Now when we're solving, we see that we get false, because this solve is specifically looking for real solutions. So in the catalog, there's actually another possibility, and it is called C solve for complex. So you can go to C and scroll up, down, or D and scroll up. I think it might be faster to get to C solve from here. Or we could have simply just taken the previous solve and edit it by putting a C in front. And now we see we get the same solutions, -3 plus I root 23 all over 4, or -3 minus I root 23 all over 4. Now there's something interesting about these two numbers because we have a plus here and a minus here. These two numbers are special because, I'm just going to take a screen snapshot of these two. These two numbers are special because they have the same terms but opposite signs for the imaginary part. We refer to numbers such as these as complex conjugates, and that's because they multiply together, back together, to give us a real number. So just to confirm our solutions here, and I'm just going to write what I said there about complex conjugates. We have the opposite sign for the imaginary part. So in general, if we have a plus bi and a minus bi, these two numbers, these two complex numbers, are complex conjugates. Because their imaginary parts have opposite signs. And also they multiply together to give a real number. So they produce a real product. If a number is real, then the imaginary part is not there, so the imaginary part is 0. All right, before we move on to the next example, I want to take a look at some powers of the imaginary number I. So if we look at I to the exponent 1, then that's defined to be -1. Well, we will just refer to that as I. I squared we saw as -1 because we square this and we get the -1. I cubed is I times I squared. So when we have I times -1, we get -I. I to the 4 is I times I cubed, which would be, I'm just going to refer to this as I again, I times I cubed, which is I times -I, which equals -I squared, but I squared is -1, so this is equal to +1. Now let's continue on a little bit more. I to the exponent 5 is I times I to the 4, which is going to be I times +1, which is I. I to the 6 is, well, there's lots of ways we could do it. We could say I cubed times I cubed, or we could say I squared all cubed. There's lots of possibilities. If I use the I squared all cubed, then I replace I squared with -1, and I get -1. If I took I to the 7, I could say I cubed times I to the 4, because my exponent law says keep the base and add the exponents. So I cubed we know is -I. I to the 4 is +1, so we get -I. And we'll just do one last one. I to the 8 is let's say I squared all to the exponent 4. We could say I times I to the 7, I squared times I to the 6, I cubed times I to the 5, or I to the 4 squared. Well, let's do it that way as well. I to the 4 squared, well, I to the 4 is plus 1, squared is plus 1. Okay, let's move on to the next example. Number 3, solve for the real constant k such that this quadratic has 2 real roots, 1 real root, no real roots, and state a condition such that the roots are rational. Well, if we want 2 real roots, then we know that the quadratic discriminant must be positive. Imagine that we've got a quadratic and its graph is a parabola, so it's either concave up if a is positive, or if a is negative, we have a vertical reflection and the parabola is concave down. To have 2 real roots, we want the x-axis to intersect the parabola, or the parabola to intersect the x-axis in 2 places. This occurs when the discriminant is greater than 0. Well, what we need to do for this quadratic expression, on the left-hand side is the quadratic expression, we need to work out the quadratic discriminant. So b squared minus 4ac is equal to k squared minus 4 times 1 times 4, so the discriminant is equal to k squared minus 16. So in part A, we want 2 real roots. So therefore, the discriminant must be positive. So k squared minus 16 must be positive. And now I'm going to solve this nonlinear inequality from a graphical perspective. If I have the graph of, let me put it under here. I'm going to rearrange this a little bit. Let's say that we have k squared, I'll use green and blue, k squared greater than 16, so this becomes a system of 2 equations. We've got y equals k squared, and we've got a horizontal line y equals 16. So if we are taking a look on a graph where the horizontal axis is the k-axis instead of x here, and the vertical axis is y, then the graph of y equals k squared is a parabola, 0, 0, right or left 1, up 1, right or left 2, up 4, right or left 3, up 9, right or left 4, up 16. So I'm not going to actually plot the parabola so carefully because I know when I plot the horizontal line, y equals 16, that I can work backwards to get the intersection coordinates. So I know these 2 graphs intersect when the k value is positive 4 or negative 4. I don't want the 2 graphs to be equal in height, so I do not want to include the points of intersection. I do want to talk about where the graph of the parabola, in green, is higher than the blue horizontal line. And that occurs at this portion of the green graph or this portion of the green graph. Not to leave the horizontal line out, we want the horizontal line to be lower than the parabola, which occurs on this part or this part of the line. If I take the sunshine and cast a shadow, then the shadow will be cast when x is less than negative 4 or when x is greater than positive 4. So my solution, in other words, the solution to this inequality says that k is less than negative 4 or k is greater than 4. Well, this seems completely unrelated to the original question. Let's take a look at the real constant k. Let's substitute this 0 back for y, so that when y is equal to 0, it means on the graph we are looking at x-intercepts. And if we substitute y for 0, and then choose a k value that is in our set of less than negative 4 or greater than 4, how many x-intercepts do we expect our parabola to have? Again, we took the 0 from the equation and back replaced it in terms of y, so that we know that when y is 0, we are looking for x-intercepts. So if I choose a k value, let's say of 6, which is in fact greater than a k value of 4, how many x-intercepts should my parabola have? Well, my parabola in fact has 2 x-intercepts, which is 2 real roots. And that's exactly what we would expect. Let's take a k value of -7, and we get 2 x-intercepts as well. But what happens if we take a k value of exactly 4 or -4? In this case, how many x-intercepts are there? We see only 1. And that is what we're looking for in part B. So what is the condition for part B? We want 1 real root, so the discriminant in this case has to be 0. Let's look at this from the point of view of the quadratic formula. When we are solving ax squared plus bx plus c equal to 0, when we are solving for x, we get x equals -b plus or minus the square root of b squared minus 4ac all over 2a. The plus or minus comes after the square root of the discriminant. So our 2 roots are x equals -b minus the square root of the discriminant all over 2a, or root 2 is equal to -b plus the square root of the discriminant all over 2a. If the discriminant is 0, then the square root of 0 is 0. So -b minus 0 or -b plus 0 would still be only one answer, -b. And we wouldn't get 2 different roots, we would only get the one root of -b over 2a. But it would be a double root. And a double root of the parabola occurs when we take the parent function, y equals x squared, and we simply translate it to the right or to the left. And it could also be concave up or concave down, depending on what the value of a is, positive or negative. But we would only get one root, and that would be the case when the vertex lies on the x-axis. So we should be making the connection that the vertex of y equals ax squared plus bx plus c lies on the x-axis when the quadratic discriminant, b squared minus 4ac, is equal to 0. So now we can solve part B of the question. Part B says if we only want one real root means that the discriminant is equal to 0. And so the discriminant we found was k squared minus 16 equal to 0. We don't need to think graphically to solve this, but we saw from the graph already that k would be plus or minus 4. So again, looking at our graphing program, I'm just going to put a value of -6 in here and show that we in fact got 2 real roots. I'll add this to the lecture notes. And I'm also going to take a value when k was greater than +4, such as +10, let's say. And we see that in fact we do get 2 real roots for this value of k. Okay, and we add that to the lecture notes. And then let's come ahead and we find that when k is equal to plus or minus 4, we end up getting 1 real root. So let's take a look at when k is +4, 1 real root, and sure enough, the vertex lies on the x-axis. I'm going to do that again. I don't want that thing in the bottom. And I'll make these pictures quite small and put them on the same page. Or if k is -4, we also get 1 real root. And the vertex lies on the x-axis. So this all occurs when the quadratic discriminant is 0. Lastly, we're going to take a look at the case where we have no real roots. In other words, we want to have our concave up parabola with a vertex that is higher than the x-axis, so that the graph does not intersect the x-axis. So the last case, we don't want to have any x-intercepts, so no real roots corresponds to no x-intercepts of the graph y equals x squared plus kx plus 4. And we know that this was going to happen when the discriminant is negative. So our discriminant is k squared minus 16. We want that to be less than 0. So we want k squared, which I'm going to put in green again, We want k squared to be less than 16. We already had the graph drawn, but I will draw it again quickly so that it's on this page. Okay, so here we have our x and y axes. K squared is k is the horizontal variable, and y is the vertical variable. K squared is our basic parent squaring parabola. Y equals 16 is this horizontal line. They intersect when k is either -4 or +4. And what values of k makes the parabola lower than the line or the line higher? Well, the parabola is lower on this portion here of the parabola, and the line is higher on the same interval for x, which is between -4 to +4. So our solution is k is contained from -4 to +4 inclusive. And we'll just draw a quick sketch. If I choose a k value in between -4 and +4, let's choose -1, then in fact we have no x-intercepts of this graph. And therefore no x-intercepts means no real roots. So we only have complex roots here. So let's just take a quick look at what happens if we change the values of k one by one. If I change this from -1, let's go down to -2, to -3, to -3.4, to -3.5, to -3.6. As the k value is getting closer and closer to -4, the parabola is getting closer and closer to the x-axis. And therefore, we are getting closer and closer to having a real root. Let's go back to 3.95, and let's zoom in just to be clear that that graph is not touching. Okay, but as soon as we change this to -4, we do have one real root. And if we make this -4.1, we get 2 real roots. Okay, let's move on to the next question. Determine the complex conjugate of the following. The complex conjugate is often written for a plus bi as a plus bi with a bar over top. And this means a minus bi. A lot of people mistakenly think that the complex conjugate, you just change the middle sign. But that's not true. You change the sign of the imaginary term. So in part A, the complex conjugate of 2 minus 3i, I'm going to write that with a bar over top. So this says the complex conjugate of 2 minus 3i equals, change the sign of the imaginary part. So it becomes 2 plus 3i. In part B, we have 2i minus 3, and so its complex conjugate, we would change the sign of the imaginary part. So we get negative 2i minus 3. Well, people might want to write this with the real part first. Negative 3 plus 2i has a complex conjugate of negative 3 minus 2i. So we're just switching the order of these terms. In part C, we have a number negative 5. And if we write that negative 5 as negative 5 plus 0i, we can then say that the complex conjugate of negative 5 plus 0i equals negative 5 minus 0i, which is still negative 5. And so we don't have a different number for the complex conjugate if the original number is real. Again, remember that the complex conjugate of a number is the number you multiply the first number by so that the result is a real quantity. So negative 5's complex conjugate is itself because both numbers are already real. And in the last case, we have negative 5i. We can write negative 5i as 0 minus 5i, and therefore the complex conjugate of 0 minus 5i is equal to 0 plus 5i, which is equal to 5i. Okay, in the last example we have some indicated operations to perform with complex numbers. So here we're given w is 4 minus 3i and z is negative 1 plus 2i. W bar and z bar are their complex conjugates. So let's work out the real part of w for part A. The real part of w equals the real part of 4 minus 3i, and that is the real constant or coefficient of 4. In part B, we want the imaginary part of w. So the imaginary part of 4 minus 3i. A lot of people think it's the whole term negative 4 minus 3i, but the imaginary part is just the coefficient of the imaginary part. So the result from both the real part of w and the imaginary part of w are real results. So real numbers are the result of real of w and imaginary of w. Let's just take a look on the graphing calculator to see these operations in action. We can go to the catalog, and in the catalog let's jump down to R and look for RE for real. There, we can use this. RE for real just requires an expression. So, oh, I didn't put it in. I'll just type it in, RE. And the expression we had was 4 minus 3i. Now your I you can find in several different places. Here's a menu above the pi button, or with the pi button. There's your I. And that didn't like it. I think it was REAL, wasn't it? Yeah. Okay, so I'm just going to type in 4 minus 3i again. The I here and the alphabet I are not the same I. Okay, so the real part is 4. Go back to the catalog and look for the imaginary operation. Go to the I and it's just imag. So we want imag of 4 minus 3i. And it just returns the real number or coefficient of the imaginary term, which is negative 3. We can also find complex conjugate, but I'm going to leave you to look for that in the catalog and see if you can't find it yourself. Okay, I'll take screen snapshots of these to go along with the lecture notes. Okay, so let's go ahead and start working out some of the rest of these. In part C, we have the square root of negative 242. And let's take a look at the next one. Okay, so in, let's see, we're running out of room here. Part C, maybe I'll put it down here. In part C, we want the square root of negative 242. Well, the first thing I'm going to do is break that apart as, I'm going to use a proper equal sign here. This is equal to the expression of square root negative 1 times the square root of 242. 242, I can at least factor a 2 out, and I get 2 times 121. So I can break this apart as the square root of negative 1 times the square root of 2 times the square root of 121. The square root of negative 1 is I, the square root of 121 is 11, and so this is going to be 11 square root 2 I. Now it's okay to put the I at the back, just make sure it doesn't go inside the square root sign. In the next case, we want to work out z over z. Let's go back to the full screen display. Oh, not the full screen display, rather. Let's go back to the single page display. And we will have to take these to the next side. I'm just going to clean this up a little bit. I seem to have this in 2 places and I don't want it there. We'll just cut that. Okay, so now we have part D is z minus 4w. Z minus 4w, where we have to recall that z is equal to negative 1 plus 2i, and w is equal to 4 minus 3i. I'll just confirm those. Negative 1 plus 2i, okay. And so this is going to equal negative 1 plus 2i minus 4 times 4 minus 3i, and it's like regular algebra, we expand and collect like terms. And we write the real part first, so negative 1 minus 16 is negative 17 plus 14i. In part E, the question says to work out w multiplied by its conjugate. So w is 4 minus 3i. Its conjugate is 4 plus 3i, and we expand the binomial. 4 times 4 is 4 squared. 4 times 3i is plus 12i. Minus 3i times 4 is minus 12i. And minus 3i times positive 3i is minus 3 squared I squared. And we see here that the terms in the middle, positive 12i, negative 12i, will cancel. So it looks like we have gotten rid of the imaginary part, but we still have this I squared. But what we have to keep in mind is that I squared is equal to negative 1, and 3 squared is 9, so this result is 16 minus 9 times negative 1, which is 16 plus 9, which is 25. And this makes me want to remind you of the special factoring that we had seen in 2.2, sum of squares. When we were factoring the sum of squares like a squared plus b squared, we can recognize that this is a squared minus negative 1 times b squared. And we know that negative 1 is I squared, and then this is times b squared. So now we have a difference of squares. Well, let me rewrite it one more time before factoring. In our difference of squares, we have a squared minus bi quantity all squared. And now we can apply the difference of squares to get a minus bi times a plus bi. We see that we have a real result up here coming from two complex conjugates. So the two complex conjugates multiply together to give us a real result. All right, let's take a look at part F, which asks for the conjugate of conjugate of z divided by z. And let's do this one here. The conjugate of z divided by z is equal to the conjugate of negative 1 plus 2i divided by negative 1 plus 2i. Well, the conjugate of negative 1 plus 2i is negative 1 minus 2i. What we want to do here, the unwritten rule, is that we want to make the denominator real. And if we want to make the denominator real, and the denominator is a complex number, we must multiply the denominator by its conjugate. So we have to multiply by negative 1 minus 2i. But you can't change the value of the blue fraction. The only thing you can multiply by is 1, which means that the numerator of the red fraction must be the same as the denominator. And so here, when we multiply, we're expanding two binomials, so we do it carefully. And we see we get negative 1 squared. So this is negative 1 minus 2i all squared, all over negative 1 plus 2i multiplied by its conjugate. And I'm just going to come over here and continue. So we get square the first, positive 1, multiply together and double. So we get positive 4i, and then square the last. So we're going to get positive 2 squared, which is 4, I squared, which I'll call I squared for now. And in the denominator, we know that the middle term is going to disappear, so all I really need to do is multiply first times first and get positive 1, and last times last, which is going to be negative 4i squared. Now, you can't do any canceling here because the only way to reduce fractions is by factoring, so we'd have to have common factors. We are not factored, we are adding terms. So I'll just simplify here. 1 plus 4i, I squared is negative 1, and therefore this last term is negative 4. All over, this is 1 minus 4 times negative 1. So this is positive 4 plus 1 is 5 in the denominator, and in the numerator we have negative 3 plus 4i. So if we wanted, we could write this as negative 3/5 plus 4/5 I. You can check this on the calculator. Please find the feature to do this on the TI Inspire. Let's take a look at the next example. We want to look at I plus I squared plus I cubed plus I to the 4. I think I'm going to leave some of these problems for you to try and compare your answers on the TI Inspire. So let me put a little box around these. I want you to do these for homework and check with TI Inspire. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.